by Christian Nilles, who will continue a description of the same chemical system, but from the very drastically different point of view.
Thank you for the intro, Dimitri. So, as you were saying, I am now studying the same type of reaction, but through Marcus theory. To start off, Marcus theory was first conceived of by Rudolf Marcus in 1958, and it was used for to look at the electron transfer of inorganic, organic metallics, and organic molecules. Here's just a general description of what a Marcus theory graph would look like. We have two different potentials, which both would correlate to a molecule. One would be an acceptor and one would be a donor. And what we're looking at is this intersection by these dotted points that it will be like the activation barrier in like the graph, the common graph we'll see, except this is just the energy we're trying to overcome the transfer of this electron from the acceptor to the donor. This gap, the HAB or 2HAB, is it's called I'm trying to remember the word. But what it means is the smaller this gap is, the less likely that the electron would be stick to the lower potential. But the wider the gap this becomes, the easier it is for the lower potential electron to jump back to the higher potential. So the substrates, as we discussed before, are a lead halide perovskite and an organic dye of tribenzylamine. We had two different types of the dye. We had the unfunctionalized one, which was just the tribenzylamine, and then the functionalized one with the methanol group. So these are just the substrates we're using. And then the very bottom here, we're showing what the type of scenarios we're going through of a through space interaction and a bond interaction between the methanol group to the perovskite. As you see that the perovskite is donating to, will be donating a proton to the dye while the electrons go into the perovskite.
Not proton, hole.
Hole. Okay. So the parameters for this, we're looking at mainly at the bond lengths, or I shouldn't call it bond length, but the distance between the perovskite and the dye. And for the chemical bond, it would be 0.64 angstroms, while the through space length is 0.24 angstroms. And as for the experiment, I started at a momentum of 50 just to see where to start. But I jumped up to 90 because that is where I decided that the best optimal electron transfer starts, and I incrementally increased by 10 to 130. So here's the chemical bond scenario. I simplified the Marcus theory due to its more of a learning experience. So I set both the energy potentials to 0, so there is no offset. And I also made both the curvatures the same for each one. So this is not the true scenario between the two. The only thing that's mainly true to it is the length between the dye and the perovskite. So as we are looking at the initial momentum of 100, which is on the optimal yield I saw of the electron transfer. This moving part is the electron. And as you can see, every time it passes its intersection point, there's enough energy to transfer over some of the electrons into the acceptor. And as over time, you will see this will increase. So then we also moved on to the through space. There's a smaller gap between the dye and the perovskite. So there would be a lower activation due to the intersection point will be lower down on the energy potential. So as you can see, we start having a faster churn of electron transfer. So to determine the yield, we did transmission probability, and here's the graph of that. That's just taking the integration from the intersection point to the left and right. The left would be the product and the right would be the reactant. And I decided to take the yield right around the 3 point. And as you can see over time, we have an increase in yield, meaning electron transfer was being achieved over time. Here's just a larger rate of scenarios. In this, you will also see the rate of the reaction. And from what I see, this is the chemical bond, and this is the through space. And you see that the rate of the reaction at 50 does not achieve, but in the through space, the momentum of 50 is enough to start transferring the electron over. It's with also a higher rate, but it decreases as you increase the rate. So we also are looking at how the electron shell shifts, because every time you move the electron over, it would shift over time. At the momentum of 50, you'll see because there's no electron transfer, the shell never shifts. While when I increase it to 130, over time, due to more electrons moving over, you will start seeing a shift over time. And here's just a plots of the rate versus kinetic energy. And as you increase, we'll see a quick increase in reaction rate through the through space, which is circles, and these triangles are the chemical bond. And you can see a faster rate increase, and the chemical bond is just faster overall through the whole scenario. So in conclusion, the chemical bond has a faster reaction rates than the through space, but the through space has a quicker reaction rate increase. Higher reaction yields yield further electron shifts, and there's a point in which yields start to decrease because the momentum overpowers and the electrons are able to jump back and forth between the donor and the acceptor. We're looking at a very simplified version of this scenario due to just a learning experiment.
Okay, let's thank Christian.